So let's continue our discussion on the ability of solid objects to stretch. Now earlier we said that the force we apply on the object is directly proportional to the distance our object elongates. Now something else also influences the amount our object stretches, and that is the type of material that our object is composed of. So let's look at the following equation. This equation gives us the amount our object elongates when a certain force is applied to that object. So our change in L is simply our elongation distance of the solid object. Our E is simply known as Young's modulus. It's a constant that depends on the type of object we are using. Now E is independent of the shape and size of our object, and it only depends on the actual material that the object is composed of. For example, marble objects and steel objects will have different E values. Now, F is simply the force we apply on the object. The A is the cross-sectional area of the object. And L naught is simply our initial length of the object before the object stretches. So let's look at the following example in which we're going to apply this formula. A 2-meter long steel piano wire has a diameter of 0.3 centimeters. Find the tension in the wire if that wire stretches a distance of 0.6 centimeters. So we basically want to take this formula and solve for the force. And we see that force is equal to change in L multiplied by A multiplied by E Young's modulus divided by the initial length of the object. So we know the initial length of the object is 2 meters. And we can find the area by simply realizing that the wire is circular, and so that means to find the area of the cross-sectional area of the wire, we simply take pi and multiply by the radius squared. So the radius in this case is simply half of this quantity, 0.15 centimeters. Now to convert it to meters, we divide by 100, and we see that our radius is 0.0015 meters. We square that and multiply by pi. And the quantity we plug into this A. Now E we can simply look up in a textbook or online, and we have 200 times 10 to the 9 newtons per meter squared is the value for E. Now the change in L is simply this quantity divided by 100. So 0.006 meters. So we multiply and divide and we get a quantity of 1,350 newtons is the tension in our steel wire. Now, let's examine something known as stress and strain. So let's look at this formula once more and let's solve for E. If we solve for E, we see that E is equal to, well, we have a fraction. We have the numerator, and inside the numerator we have force per cross-sectional area, F divided by A, and this numerator, F divided by A, is known as stress. Stress is the force applied per cross-sectional area on the object, and it has the units of newtons per meter squared because force has newtons and area has meters squared. Now, what about our denominator? The denominator is simply the ratio of the change in length over the actual length of the object. And because this has unit meters and this also has unit meters, the meters cancel and the denominator becomes or is unitless. And this denominator is known as strain. So stress is the numerator of the fraction and strain is the denominator. So let's look at the following example. Let's suppose a marble column of cross-sectional area of 2.0 meters squared supports a mass of 30,000 kilograms. So in part A we want to find the stress, and in part B we want to find the strain. To find the stress, we simply take the force that acts on the object and divide it by the cross-sectional area. So we know what the mass is and we know what the cross-sectional area is. to find the force, we simply realize that the force that's acting on the mass is the force of gravity. So that means force is simply mass times g, our gravitational constant. So mg divided by A is 30,000 kilograms multiplied by 9.8 meters per second squared. Divide that by 2 meters squared, and we get 147,000 newtons per meter squared is the stress. It's the force per unit area. Now we want to find the strain. We're going to use this formula to find the strain. So we want to find the denominator of this fraction. So we bring this quantity over to this side, we bring the e to the right side, and we get that our change in L over L naught, our strain, is equal to force per unit area. So the stress, and divide that by E, or multiplied by 1 over E. Now we can simply find E in a textbook for our marble object, and E is 50 times 10 to the 9 newtons per meter squared. So we simply take 147,000, the quantity we got from part A, our stress, and divide that by Young's modulus for marble, and we get 2.9 times 10 to the negative 6 meters. So this is our strain of the object. It's the ratio of the change in length to the original length of our object.